This is 8.4, which is rules of derivatives, and we're going to take a look at 3 rules of derivatives. But before we do, let's review where this derivative idea comes from. We started with the idea of changing slope, and we had this model that looked something like this. And so that'll give us an approximation of the slope at the point x. To get the exact slope at a single point, we take this and we apply the idea of a limit. We take the limit as h approaches 0. So we want to take this length h and we want to squeeze it down all the way to 0. This definition, this guy right here, will give you the equation of the slope. It describes how the slope behaves. F of x is equal to 3x squared plus 2x plus 5. And if we wanted to find f prime of x, now f prime of x is the slope equation. So we'll call this, it's called the slope equation. It's also called the derivative. And you calculate this by using the difference quotient. In order to find the first derivative, or f prime of x, we're going to use the difference quotient. And I'm not going to go through all the arithmetic of working this out. There are 2 nice things that are going to happen that you can anticipate happening. The first nice thing is that f of x is going to cancel. So you know that this 3x squared is going to cancel with something over here. You know that 2x is going to cancel with something over here. And you know the 5 is going to cancel out with something here. So f of x will cancel out completely. The second nice thing that will happen is that h will cancel as well. When you get done doing number 1 and canceling all that stuff, every term in the numerator will have an h in it. All the time, guaranteed to happen. You factor that h out, and then you cancel with the h down here. And now you can apply the limit as h goes to 0. Prior to this, you can't do the limit, because that would mean putting a 0 in the denominator, and that would make everything undefined. So we first have to do step number 1, cancel everything out. Then we have to do step number 2, cancel the h's, and now we can apply the limit. So I guess step 3 would be apply limit as h goes to 0. And then once you do that, you will have f prime. So this thing is going to shake out to be, if we were to do all of this mathematics, if we were to do it, you would get 6x plus 2 plus like 2h limit as h goes to 0. And then when you plug in that 0, this term is going to cancel out. And so you'll be left with 6x plus 2. This is the formal, long way of doing it. There's also a shortcut. And we talked about doing the shortcut as well. And we're going to solve this equation using the power rule for derivatives. Power rule for derivatives said you take this exponent, you multiply it by the coefficient, so you get 6x, and then you subtract 1 from that exponent, plus 2. So this is applying the power rule for derivatives. This is much more efficient than doing the whole difference quotient, bless you. When you do the difference quotient, you've got to write out all this stuff, you've got to do all this arithmetic, and it turns out that the difference quotient and the power rule will give you the same answer for polynomials. So if we wanted to write the power rule more formally, we'd say this. If f of x equals a times x to the n power, then the first derivative is equal to a times n x to the n minus 1 power. So let's say that f of x is equal to a of x times b of x. So this is going to be 2 functions that are multiplied together. Then the derivative, f prime of x, is equal to, and what I'm going to do is I'm not going to write this with the a of x. I'm just going to write a, okay, if that's all right. It's equal to a prime times b plus b prime times a. And this is called the product rule for derivatives. Sounds like you want to do an example. Okay, so let's say f of x is equal to 3x squared times 2x squared plus 3x plus 4. And this first part, we'll call this A, and we'll call this part B. Okay? So we've got two functions that are multiplied together. The derivative of this function is equal to A prime times B plus B prime times A. So let's figure out what these are. What is A prime? 6x. Times B. So B is 2x squared plus 3x plus 4. Plus, what is B prime? So you got to take the derivative of B, 4x plus 3, and multiply that by A, which is 3x squared. But maybe we should simplify just a little bit. So this is what my final answer is. If you simplify it all the way down, this is what the first derivative is equal to. The reason I picked this function is because I'm going to take our original function and actually, instead of writing it as two things multiplied together, I'm going to multiply it out. And if you apply the power rule to this guy, what do you get?
The one in the blue.
Yeah, well, let's pretend we don't know what the one in the blue is. So take the derivative of this first part, 24x to the third. Take the derivative of that part, 27x squared. Take the derivative of this part, 24x. And is that the same as what we did the other way? Yep. Take the derivative of the first times the second, and then add to that the derivative of the second times the first. So here's another one. F of x equals A of x divided by B of x. And you want to take the derivative of this function that is basically two functions divided by, one divided by the other. So f prime of x is equal to A prime times B minus B prime times A, all divided by B squared. And this is called the quotient rule for derivatives. So let's say f of x equals 2x squared plus 5 divided by 3x plus 2. And so this is going to be A, this is going to be B. So the first derivative is equal to A prime times B minus B prime times A, all divided by B squared. Now what some students like to do is once you identify A and once you identify B, go ahead and take their derivatives. And so we know that A prime is equal to 4x, and we know B prime is equal to 3. You just take those values, substitute them in, and evaluate it. And you can leave your answer in this format. Leave it in unfactored format. You do not need to simplify this. So 8.5 starts talking about applications, and really the best application for derivatives and their functions comes from, we'll do this scenario, dropping objects from very tall buildings. When you start dropping things from tall buildings, you start noticing some things that we can measure about that object as it's falling. And there are three things that we can measure about this object. We can measure its position, we can measure its velocity, and finally we can measure its acceleration. An acceleration is a description of how is the speed changing. And let me build up to this. The velocity, or we'll start with position. Position is the height, how high something is. Velocity or speed is a measurement of how the height changes. So if your position is changing quickly, then you'd say something's moving fast. If your position is changing slowly, then you'd say something's moving slow. It's slow speed. Acceleration is a measure of how the velocity changes. So there are three things that we can measure: position, velocity, and acceleration, PVA. Let's say that you have a position function, and we're going to say, what is the height at time t? So let's say we give you an equation that describes the height above the ground of an object as it travels. Maybe something like x squared plus 2x plus 5. Let's say this describes the height of an object, okay? Well, how would we describe its velocity? So the velocity function is equal to h prime. It's equal to the first derivative of the position function. So the velocity function is 2x plus 2. If you want to know what the height of the object is at time 0, plug in 0 to the green equation. If you want to know what the height is at 10 seconds, plug 10 into the green equation. If you want to know what the height is after 25 seconds, plug in 25 to the height equation. If you want to know how fast it's going, what the speedometer on the object says, then you plug that time value into the blue equation. That'll tell you how fast it's going. And then if you want to find out how it's accelerating, well, that is equal to the second derivative of the height function, or the first derivative of the velocity function. I changed my variables. I should have been using t's all along. Anyway, that's equal to 2. So this is how position, velocity, and acceleration are related to each other. They're derivatives of each one. Here's the position of an object. So to find its velocity, take the first derivative. To find the velocity at 3 seconds, take 3 and plug it into the first derivative. Bloop. There's the first derivative, velocity function. How do you find the acceleration? Take the derivative of this, 36t.